So thanks again for the organizers for allowing me to do this talk. And so today I'm going to present a bit some work we've been doing with my colleagues Niraj and Alham in the University of Edinburgh. And it concerns the efficient construction of quantum physical unclonable functions with unitary tdesigns. And for those of you who are interested in reading a bit about the paper, it's available on the archive at this address, basically. So just a bit of outline about what this talk is going to be about. So I'm going to start with what is called the classical physical unclonable function, or the Cpuff. I'm going to discuss a particular construction and its properties, as well as its drawbacks. I'm then going to transition to quantum physical unclonable functions, or QPUFs, which are basically the main goal of our work in some sense. And I'm going to mention the previous constructions and their drawbacks as well. And then I'm going to discuss the main technical tool which we use to construct our version, or at least the way we see QPUFs, which are unitary tdesigns. And in particular, we're going to focus on a specific branch of these, which are the unitary tdesigns which are generated via measurement-based quantum computing, or MBQC. And then I'm going to describe in a bit of detail what we've done, so how we've constructed these QPUFs with unitary tdesigns, as well as their robustness to a particular type of error. And I'm going to end with a few open questions. Great. So what are Cpuffs, or classical puffs? The way you can think of Cpuffs are they're a sort of hardware which is difficult to clone. And the difficulty in cloning is actually due to a sort of manufacturing process. And these Cpuffs gives rise, so this sort of unclonability gives rise to certain cryptographic advantages which you can use. So similar to how one-way functions which are based on hardness of certain statements in number theory, these sort of hardware Cpuffs give rise to functions whose hardness is based on the unclonability of this hardware. And so I think the simplest way to kind of picture it is through an example. So one particular example of a Cpuff, or a classical puff, is a sort of plastic token, let's call it, where inside this plastic token you have you've embedded some glass spheres. And so these spheres, they have an average radius and they have an average size and diameter, and they're dispersed in some way inside this plastic. And the puff by definition, or the Cpuff by definition, is queried by an input which we call a challenge, and provides a unique response to this input, which we call a response or an output. And in this case, in this particular example, the input is the angle of incidence of the laser beam, and the output is the interference pattern, which you get when you shine the laser through the material, when the laser interacts with the material. And so the claim is that it's extremely difficult to clone this token, and this is what is called the unknownness property. And the difficulty in cloning this token is because So it's in particular because of the manufacturing imperfection. So it's very difficult so even if you use the same manufacturing process, it's very difficult to kind of create a clone where the exact same glass are distributed in the exact same way inside the token. So this is what is called the unknownness property of the puff. Another property, which is called uniqueness, this relates to kind of how if you manufacture your puff in two different ways, how basically different your input and output pattern would be. So in this paper which we cited, the science paper, it is shown that small variations in the manufacturing process actually create different challenge response pairs. So this is called the uniqueness property. The third property is that if you query the puff with different challenges, so different angles of incidence, it will give you a different response. And this is called the collision resistance property. And the final property which the puff should verify is the so-called robustness property. So if you query it with the same challenge, which is the same angle of incidence of the laser beam, you should expect to get the same speckle pattern, or the same interference pattern. And you can do this up to some error correction. So you can add a bit of error correction to whatever puff you have, and you can get this. So yeah, just to summarize, so the puff should have 4 properties. So unknownness, which is basically unclonability; uniqueness, which is basically 2 puffs which went through the manufacturing process give you different challenge response pairs because of manufacturing imperfections; collision resistance, which is basically different challenges give you different responses; and robustness, which is the same challenge should give you roughly the same response. And so these these classical puffs have found numerous applications, in particular in some sort of crypto applications such as identification and secret key generation. And I'm going to focus now a bit on identification because I feel this is sort of a bit of important to sort of motivate in some sense. And what an identification protocol does is that you start out with a server, which say is a company which manufactures phones, and you have a client, which is the person who buys the phone. And the server wants to authenticate that the client is a valid client and not actually an adversary, which is trying to cheat it and access its services. And so what happens is that the server manufactures a puff, and it records in a secure repository a set of challenges and their responses. And then it sends the puff to the client. And whenever the client wants to validate, what would happen would be that the server chooses a random challenge from its repository and sends it to the client. And then the client uses his puff to output a response. And if the client is malicious because of the unclonability, then the response would be different to the response that the server has in his repository. And so authentication wouldn't work. Otherwise, it would be the same response and the client would be certified. And the nice thing about this is that it's actually an inexpensive solution to other sort of authentication techniques, which are based on storing secret keys securely for a very long time. So this is kind of financially costly, whereas the puff is inexpensive. So as you saw, you can do a puff by just putting some, manufacturing some glass inside some plastic, which is not very expensive. Great. So why the need to consider QPUFs or quantum puffs to begin with? Well, it's actually that these classical puffs aren't as secure as we thought they are. So they are indeed vulnerable to attacks such as machine learning attacks and side channel attacks. And this compromises their security, obviously. So one potential way to think of enhancing the security would be going to the quantum domain, where perhaps you can use certain quantum properties to get better security. And indeed, this has motivated a line of research which concerns so-called quantum puffs or quantum physical unclonable functions. Here I talk about 3. So one of them is the so-called readout QPUF, where it's sort of similar to this optical QPUF, which I showed earlier in the example, but instead of the challenge being a classical angle of incidence of the laser beam, it's actually a quantum state now. And then the response is also a quantum state. So this has been shown secure against specific, important yet specific attacks, but no general notion of security against any attack has been provided. You also have another proposal, which is based on boson sampling. And so for those of you who aren't familiar with boson sampling, it's basically one of these techniques of quantum sampling superiority, where you create a quantum circuit and it's supposed to be hard to approximate even, so its outputs are supposed to be hard to approximate even for quantum computers, and its outputs are supposed to be hard to sample for computers, efficiently generatable quantumly. So the drawback of using these sort of proposals as puffs is that it isn't very easy to certify efficiently whether you're sampling actually from a boson sampling distribution or from a classical distribution. So there are results in this direction which say that without any sort of costly communication, and if you want to do it purely classically, it's inefficient. Great. So what we're going to focus on in particular is the proposal of Arpinis et al., which is generating a quantum puff through Hardearned unitaries. So what a Hardearned unitary is, or what the Har measure is to begin with, so it's a probability measure over the unitary group. And you can think of it as the sort of, so a Haar measure is a unique probability measure over the unitary group. It's a unique probability measure over any sort of compact group, to which the unitary group is a particular example. And it is the most natural sort of notion of uniform randomness, of choice uniformly at random of a unitary. So when you want to say, I choose a unitary uniformly at random, the most natural way is through the Haar measure. And choosing randomly from the Haar measure has found a lot of nice applications in quantum information. So these applications include, but are not limited to, randomized benchmarking. They're used in black holes. You can use them in noise tailoring protocols, where you kind of have a complicated noise channel and you reduce it to something, a simple Pauli channel. You use it in these quantum superiority protocols, which I mentioned previously. We're going to use it, and Arpinis et al. Have used it to generate Cpuffs. And it's recently been used in quantum machine learning to study barren plateaus. So, perfect. So the way you define, so as Arpinis et al. Have defined this sort of QPUF, which is based on a hard random unitary. So the challenge is an input state. And we're assuming now that we have n qubits, so it's an n qubit system. So it's an n qubit input state. And the puff is unitary, which is chosen from the Haar measure, so uniformly at random from the unitary group. And the output is unitary, which is applied to the input. And this unitary is the Haar randomly chosen unitary. Unknownness comes from the fact that you can't efficiently clone this puff. And this is because the Haar measure, so there are results which say that the Haar measure, even to approximate it, it requires exponential, it requires circuits of depth exponential in n, which is the input space size. So this is kind of where the unknownness comes, or the unforgeability. So it's difficult for a quantum polynomial time adversary to clone this sort of puff. And sorry, so just to mention that the types of adversaries we're interested in this talk are quantum polynomial time adversaries. The other sort of property, which is the robustness, which basically tells you that if the challenges are close, then the responses should be close. These are quantified in terms of fidelity in Arpinis et al. Paper. So if the fidelity of two challenges is close to 1, then the output fidelity, because of the unitary invariance, would also be close to 1 with exactly the same lower bound. The same goes for the property of collision resistance, where if you have that two fidelities are far away from each other, then their response, two challenges are far away from each other, then the responses should also be kind of far away from each other. And this is yet again quantified through the fidelity and unitary invariance with the same bound on fidelities for input and output. And finally, the uniqueness property, which tells you that if you sample two different puffs from your sampling procedure, then these should be distinguishable. Their response pairs should be distinguishable. And we actually show this in the first part of our paper. So if you sample two unitaries from the Haar measure, then their diamond norm is close to 2 with overwhelmingly close probability to 1. So probability which is exponential in n, basically. And because the diamond norm is related to the distinguishability, then this means that the challenge response pairs are almost maximally distinguishable, because the unitaries which create them are maximally distinguishable. So you can go between sets of challenge response pairs and the diamond norm the diamond norm tells you a bit about the distinguishability. And the nice thing, and so actually the reason why we are interested in these types of QPUFs is because they've been shown to be secure against any attack where the adversary is allowed to query the QPUF. And the attack model which Arpinis et al. Considered and showed this for is a model where you have two phases, basically. A learning phase where the adversary is allowed to query a polynomial number of times from the puff. So when I say query, I mean give it a challenge that the adversary chooses and output a response. And then he does this a polynomial number of times for challenges which he chooses. and then he constructs some sort of database out of them. So he can maybe do tomography or quantum emulation or whatever else. And then what happens in the challenge phase is that the honest party, or the server, gives him a challenge which he chooses from the Haar measure. And then it asks the adversary to produce a response for this challenge. And then the adversary can use his database. And what they show is that the information that the adversary gathers in the learning phase is not enough to replicate the behavior of the challenge, which is chosen from the Haar measure. So more precisely, the probability that the adversary in the challenge phase succeeds in convincing the honest party that it has a copy of its puff is exponentially low in n, basically. And this sort of security scenario is relevant to scenarios of identification, which I explained a bit a while ago, but identification in the quantum setting, basically. And so these are results by Dutzi et al. Great. So this is kind of a nice way to define a QPUF, which is secure against any attack. But the only problem now is that the Haar unitary is not only inefficient to clone, but it's also inefficient to manufacture in the first place. And it's precisely because constructing the Haar measure requires exponential number of resources. So our solution is that, well, let's try to use an object which is indistinguishable from the Haar measure. And that's exactly what the unitary t-design is. And I'll explain a bit now in a bit more detail what unitary t-designs are. So now you're not choosing anymore from the entire Haar measure or uniformly from the entire unitary group, but you're choosing a set of unitaries, ui, with a given probability pi. So you have a set of unitaries ui, and every unitary ui is chosen with probability pi. And what you also have is that you're averaging over the sets of these unitaries. And what a t-design does, or what an exact t-design does, is that if you average up to tth order with respect to the elements of design, this is exactly equal to averaging with respect to the elements of the Haar measure. And this is quantified in this equation here. So PTT is any polynomial of degree t in the elements of the t-design, and degree t in the dagger of the elements, so the conjugate transpose of the elements of the t-design. And when you average in the following way, this is exactly equal to integrating the same polynomial with respect to the Haar measure over the unitary group. And on the other, so this is an exact unitary t-design. On the other hand, an approximate unitary t-design, this sort of equality or something similar to it holds approximately up to a factor epsilon, basically. And the applications of t-designs are basically most of the applications of the Haar measure can be translated to applications of the t-design. So the t-design can replace the Haar measure as an efficient alternative solution in the tasks which the Haar measure is usually used. So yeah, just to say that the main reason why we're motivated to kind of use the t-design is that there exists some efficient constructions of it. So that's the entire point. It's an efficient alternative to Haar randomness. And so unitary t-designs, which have been constructed for any t and any dimension of the unitary group, very recently we have constructive kind of circuits which give you these. But the main problem is that up until now, they're still exponential in n and in t. So n is, in this case, the log of the dimension. So it's the size of the input space, which we saw earlier. And for most applications anyway, approximate designs are enough. And these we know we can generate using algorithms which are simple and efficient in log t, log d, and t, basically. And so, of course, in the rest of this talk, we assume that d is equal to 2 to the n. So we've been assuming this for a while, but now kind of we make this concrete. So we're working with n qubit unitaries, and we're working with n qubit circuits. So circuits with n qubits as input. And we're going to focus on a specific way to generate an epsilon approximate t-design, which is MBQC. So yeah, to summarize, exact designs are cool and we would definitely like to use them, but unfortunately, the constructions up until now are not efficient for NET. So we're instead going to use approximate designs, and we're going to use this sort of MBQC formalism to construct them. And that is because this is a way we found out which would give us good uniqueness of our designs. And I'll explain a bit about this later in the coming slides. So just to show you a bit of definitions of approximate unitary t-designs here. So approximate unitary t-designs have many definitions, and the definition you use depends on the application, and every definition has its own strength and also its own cost in terms of circuit depth. So this anti-concentration definition is used in these boson sampling experiments and other sorts of quantum superiority experiments, and it's not it's not too difficult to generate. It's not too costly in terms of depth. You can do it with log n depth. These are kind of new results. But if you want to use it for more evolved scenarios, such as studying black holes or randomized benchmarking, or even generating puffs, then you have to use this additive definition, which involves the diamond norm. And then you would need something which is polynomial in n and t and 1 over epsilon to generate it, rather than logarithmic in this case. And if you want to a really strong definition, then you go with the relative definition, and that is also kind of linearly more costly than the additive definition. So linear and more costly than the additive definition, and polynomially in T. So we're going to focus on the additive definition because for our purposes it's sufficient. So as I said, we're working. The goal is kind of to find something which is indistinguishable from the Hardearned measure, and the diamond norm relates quite well to indistinguishability. So we're going to use this sort of definition encircled. And this ET is just an average of a particular polynomial. So it's kind of this guy. Cool. Great. So now just to tell you a bit about MBQC unitary T designs. So MBQC is measurement-based quantum computation. It's a different sort of model to the circuit model. It's computationally equivalent, but the assumptions are fundamentally different. So in the circuit model, you have a set of gates which kind of build up your entanglement as you go. Whereas in MBQC, you start out with all the entanglement in the beginning, and then you perform local measurements. So more particularly in MBQC, you start out with what's called the graph state, which is this big entangled multipartite state, and you perform measurements on a part of it. And the unmeasured part, and by performing local single qubit measurements on part of the graph state, what you do is that you teleport information to the unmeasured part of the graph state. And this is how the computation proceeds, basically. So you teleport the state onto the unmeasured output, and also the measurements induce some sort of unitary, which is applied on the output when you do them in a specific ordering, and you correct for the randomness of the measurement results. So just to give you just a simple example of how we're going to use MBQC. So consider this sort of 2-qubit example where you have an input qubit and an output qubit, and they are entangled by an entangling gate. And what we're doing is that we're measuring the input qubit at an angle alpha in the XY plane of the Bloch sphere. And what this does effectively is two things. So it transports the state of the input, so the state of this qubit, onto the unmeasured output. And it applies at the level of the output this unitary, which is just Hadamard, Z phase to the power m, and Z alpha. And these are the kind of definitions of these matrices. And this m, it depends on the measurement result. So in this sense, we can think of this um as a sort of random unitary, which depends on the measurement result. And now, usually in the usual MBQC, to get a deterministic computation, you'd usually employ some sort of corrective strategy precisely to cancel out these random m's, these random z's which pop out, and get a deterministic computation. But here, rather, we're not going to correct for them. We're going to do measurements non-adaptively. And this is precisely because it is this randomness which we will use to generate the approximate design. So this same idea, which you saw for the 2-qubit gadget here, but applied to larger graph states, is the way we generate designs or epsilon approximate T designs. And we showed in a bunch of papers that if you have a big enough graph state, a cluster state usually, so it's kind of a regular lattice graph state. And by big enough, I mean polynomial in n, and in t, the order of the design, and in log 1 over epsilon. Then you can, if you measure all but a subset, you would effectively get on this subset an element of an epsilon approximate t design. But the angles where we measured were very particular. So they were very particular choices of XY angles. But in this work here, we're going to actually use angles which are uniformly chosen from 0 and 2 pi. And we can do this because of a recent relaxation by Osmaniak et al., which is a relaxation in the circuit model construction of designs, but can be used in MBQC. And I'll show you in a bit how, I mean, how actually we generate designs in the circuit model and how we can go to MBQC. Perfect. So let's just consider first this sort of figure to the left. So this is a particular construction or part of a construction for a T design in the circuit model. So this is called the parallel local random construction. So at every depth 1, so this is kind of a depth 1 layer of the circuit. What you would do is that you would either apply a set of unitaries on qubits 1, 2, 3, 4, 5, 6, or you would apply on qubits 2, 3, 4, 5. So this we call an odd application, and this we kind of call an even application. So we'd either do an odd application or an even application at each depth 1 layer with probability half. And if you do this long enough, and by long I mean polynomial in n and t and 1 over epsilon, then what you would get at the end is a unitary which is sampled from an epsilon approximate t design in the additive definition. And previous constructions, they had constraints on how you choose these unitaries. So you had to choose these unitaries from a set which is universal, contains unitaries only with algebraic entries, and is symmetric, so contains elements and their inverse. And that's why I was saying that previously, when you wanted to translate it to MBQC, it was very particular. But now with the relaxation of Osmaniak et al., they actually showed that all you need is universal. So you don't need algebraic entries and you don't need inverses. And this is actually what we're going to use. And the way you can translate a 2-qubit gate onto MBQC is by using this simple kind of gadget here, this simple 2-qubit gadget. So this simple 2-qubit gadget, which works in the same way as our example, it generates this random unitary here. So this is a CZ. This is an X alpha, which is basically this guy, but with Hadamard before and after. And this guy is the Z alpha, is this. So, and you can easily show that this is universal, so that's fine. So so this satisfies all the conditions of the Osmaniak et al. Construction. And so if you repeat this poly n-t times, then it will also give you an approximate T design. And you may be wondering at this point, well, okay, why did you go through all the trouble of doing this sort of construction? And I'm going to tell you now why. So in our construction, we needed the alpha and beta and gamma and delta to be chosen uniformly from 0 to pi. So that's why we chose the Osmaniak et al. Construction. Because if you choose from 0 to 2 pi, then these are not necessarily algebraic or symmetric. So we needed this relaxation. But why in the first place did we need to choose these angles from 0 to pi? And this is because this is a way we can show that we have a good uniqueness. So I'll just tell you in a bit what I mean. But just consider with me now how this kind of entire circuit translates into to this MBQC picture in some sense. So this is kind of a regular graph state, but it's an on-the-fly, it's a variable architecture graph state, because this parallel random circuit, as I said, is probabilistic. So these are applied with probability half. And in another application, it could be kind of that these are in the beginning and these are here and so on. And these angles, all of them are chosen uniformly from 0 to pi. And so the uniqueness here comes from the fact that if you have, So if you want to generate two different instances of the puff, then these angles, because two different instances of these angles are chosen uniformly from 0 to pi, will most likely not be the same. So they'll be far from each other, because at every instance you're choosing randomly and independently from 0 to pi. And therefore the unitaries that they give rise to would be far. And so this is kind of the intuition for why we chose to go with this and not with other things. So robustness and collision resistance are guaranteed from the unitarity of the QPUF, as we saw previously. So just to remember, robustness is that states which are close in fidelity give you close response. Collision resistance is the opposite. States which are kind of far in fidelity give you a bit of a far response. Uniqueness is that if I sample two different hues from my t-design, then with high probability they're distinguishable. And for our architecture, which relies on choosing angles from 0 to pi, this is what we managed to show numerically. So numerically, we ran some simulations, and with high probability, we observed most of the time, as we kind of increased the number of layers of the circuit, that the diamond norm of the difference between the two unitaries was close to 2. So that's maximal distinguishability, if you remember from the beginning of this talk. And the same holds when you kind of increase the number of input qubits n. So apparently uniqueness holds, but we didn't prove it analytically. We managed to show it numerically. Great. So robustness, collision resistance, and uniqueness. We have 3 out of 4. So what we still need now is the unknownness property. And in our scenario, so the unknownness is not due to the difficulty in cloning, because if the adversary knew the t-design is something which is efficient to generate. So it's polynomial in nt1 over epsilon. So he can do it if he's QPT, quantum polynomial time. But actually, we're going to use the fact that for an unknown unitary, so for a t-design which is a unitary which is unknown to the adversary, it is impossible if he queries it less than t times for him to be able to distinguish whether this unitary is from the Hardearned measure or from the unitary t-design. And if you remember, the way to see this is just by going back to the diamond norm definition. So the diamond norm definition just tells you that average, so the difference between the average of the Hardearned measure and the t-design is less than epsilon. And so what the adversary, so he can't distinguish them with better than epsilon in some sense. And what this translates to, so if you do a bit of math, is that if you have an unknown unitary sampled from a design and you query it up to t times, then you can't do better than distinguish it from the Hardearned measure with probability 1/2 plus epsilon over 4. And if epsilon is low enough, then that's doing no better than guessing, actually. So you're just guessing. So that's the best you can do, is that you can guess. And that's not powerful at all. And you can make this epsilon arbitrarily small. You can actually make it exponentially small in n, and it would only increase a linear overhead on the depth of your design, a linear and overhead on your design. Because if you remember, it's a function of log 1 over epsilon, the design thing. And the time t, this is kind of a cool thing we have in our construction, is that t, which is the order of the t-design, could be thought of as the time your puff can spend in an insecure environment. And the reason why this is actually true is, so the higher the t, basically, the more queries the adversary can make without being able to distinguish. And if you think of an identification protocol, you can think of it as the more time it can spend, the puff can spend in flight between the server and the client without being, and with the adversary querying it, because it's an insecure environment, and without being exposed. So the higher the t, the more time the puff can spend in the insecure environment without being exposed. And now we come to the last part of what we did, and it's the noise resilience of the QPUF. So we considered a very sort of special type of noise, which is called unitary noise. And in this case, the channel maps unitaries onto unitaries. And we also consider that the error rate of this channel is at most a constant, which is independent of the system size. So it's not a very realistic assumption. But in this sort of scenario, we can show that if PIUI is an additive epsilon approximate design, then its noisy version, PIU prime I, is an epsilon plus epsilon t approximate unitary t design. So in this sense, it's robust. because noise isn't kind of changing the T, it's keeping it a T design. But of course, if you think about it a bit, this actually means that you would need a fault-tolerant puff for this to be realizable. And so this is not very kind of, this is not realistic. So it would be interesting to see if we can add, some maybe perhaps error mitigation techniques, or even actually fault tolerance on top of the puff to kind of get, robustness to more general types of errors. Cool. So I'll end with a bit of open questions. So the first open question relates to the architecture. So as I said a while ago, so if you just look back to this architecture, so the MBQC architecture is variable because the circuit structure is variable, right? So it's a parallel random circuit, it's probabilistic. So what would be nice would be actually to have a fixed architecture where you kind of have your angles chosen from 0 to 2 pi. And this is ongoing collaboration with people from University of Berlin. Another question would be that, how do you certify that you have a T-design puff? So if the manufacturer gives me a sort of set of unitaries, how can I certify that these form a T-design, basically, broadly? And also, the way we design the T-designs now is a bit expensive, both in terms of circuit depth and in terms of number of non-Cliffords that we use, because we kind of use a lot of, like non-Clifford. These aren't necessarily fault tolerant. So could there be a way to kind of design puffs which are less expensive? And this is exactly the work of, we can maybe get insights from this paper here. And also, it would be interesting to consider Qpuffs beyond just unitary channels, just general quantum channels, Qpuffs constructed from general quantum channels. And also, as I mentioned a bit previously, if it would be possible to construct puffs which are robust to more general errors, that would be kind of nice as well. So I guess that's it for my talk. And with that, I thank you very much for listening, and I hope you enjoyed this talk. Thank you.